Monitoring requirements in systems of systems. Large-scale, heterogeneous software systems are ubiquitous in many domains. Often, such systems are part of systems working together to fulfill common goals resulting from domain or customer requirements. SOS comprise hardware and software systems that are frequently provided by different vendors following their own development strategies and release plans. SOS engineering has been compared to developing cities in contrast to constructing buildings. SOS typically aren't planned and engineered top-down, but come into existence gradually, often as the result of decades of development by independent teams. Consider an example from the automation software domain. In a steel plant, heterogeneous software systems interoperate to automate and optimize metallurgical tasks. Systems developed by different teams and even vendors interact to automate processing iron ore, melting and refining ore to produce steel, casting liquid steel into solid slabs, and producing girders, steel sheets, and other products. A steel plant SOS must coordinate material transportation, quality control, and logistics during production, and it controls hardware such as torch cutting machines, transport vehicles, or robots. The correct interplay between the software and hardware systems is crucial to guarantee continuous, uninterrupted production and high-quality products. So it is essential to ensure that an SOS complies with its requirements. Such SOS requirements are owned by diverse stakeholders and exist at different levels for different systems and in different artifacts. They often overlap, cross-cut, or even conflict, and allocating them to specific systems or components isn't always possible. Furthermore, requirements stem from physical processes, resulting in a need to carefully consider the dependencies between software and hardware. Also, an SOS full behavior emerges only at runtime when the evolved systems interact with hardware, third-party systems, or legacy systems. Thus, SOS engineers must monitor if and how the SOS meets its requirements at runtime, for instance, to verify components' correct timing or measure performance and resource consumption. Monitoring can happen continuously at runtime to give instant feedback on behavior violations or post-hoc on the basis of recording event traces and data logs. The challenges of SOS monitoring. As Neil Maiden pointed out previously in this magazine department, software systems generate various events which can provide data that can be used to test for requirements compliance. SOS engineers need tools that capture these events and data across the SOS to monitoring the requirements. For example, the hardware automation layer in the steel plant SOS provides sensor data and machine information such as the blast furnace temperature, the speed of the strand moving in the casting machine, or the pressure of the nozzles spraying water on the cast steel. So, optimizing steel quality relies on data on the strand speed provided by the sensors in the rollers pushing it forward, data on the temperature provided by sensors in the mold, and information about the material mixture provided from analysis systems. Collecting and interpreting this data is vital, for example, when calculating the optimal amount of water to spray to cool the steel. The complexity and heterogeneity of SOS complicates runtime monitoring requirements. As our steel plant example demonstrates, monitoring must occur at different layers and levels of granularity, and it relies on collecting different kinds of events and data from multiple sources. For instance, retrieving information about inter-system communication in an SOS requires instrumenting diverse system interfaces. Checking inter-process communication requires analyzing the interactions between the involved processes. So, monitoring must work across systems because SOS requirements can't be allocated to single systems or components, as we mentioned before. Instead, properties must be checked across the boundaries of multiple constituent systems. This problem goes hand in hand with instrumenting heterogeneous domain-specific technologies in architecturally diverse systems. Whereas developers can, for example, use techniques such as aspect-oriented programming To instrument mainstream programming languages without manually modifying the code, instrumentation for legacy systems is much harder. Also, different types of requirements must be checked at runtime, including global invariants, range checks of variables, temporal constraints on events, or architecture rules constraining component interactions. Finally, SOS exists in many different versions and variants, owing to the continuous independent evolution of the constituent systems. Adaptation and reconfiguration of monitoring solutions thus becomes essential. Reminds. In response to these challenges, and on the basis of industrial monitoring scenarios, we have been developing Reminds, the requirements monitoring infrastructure for diagnosing systems of systems. Engineers can use it to instrument systems in an SOS, to extract events and data at runtime, and to define requirements as constraints to check expected behavior and properties. Reminds can also visualize and explain requirements violations to facilitate diagnosis. Reminds has been applied to monitor requirements at different layers of a steel plant automation SOS. During continuous monitoring, events and data from different systems are collected at runtime and checked immediately to determine requirements violations. This lets engineers inspect certain components' timing on the fly. For example, the optimization system for continuous casting must finish an optimization calculation X seconds after the steel plant operator or another system in the SOS triggered the calculation. Checking this behavior requires instrumenting several systems in the SOS, such as the optimization system and the human-machine interface, which have been developed using Java and .NET. For this purpose, Reminds supports cross-system and cross-technology instrumentation and analysis of events and data. When online monitoring isn't possible, for example when a problem emerges at runtime for which engineers haven't yet defined a constraint, Reminds supports capture and replay. Engineers can use captured event traces from the system and replay them using their existing simulators to reenact what happened in the SOS. Reminds also supports capture and compare analysis of recorded event traces, which are particularly useful to support evolution. Specifically, industrial SOS components are frequently upgraded, for example during plant modernization. Such selective upgrades can have unforeseen effects on the SOS overall behavior. Reminds thus can capture event traces before and after an upgrade and compare them to compute and visualize differences in behavior. The shift from statically defined requirements toward requirements as runtime entities, for example as in current cyber-physical production systems, will continue. So, requirements will increasingly become ubiquitous throughout the software lifecycle. Consequently, the development of solutions to monitor requirements of SOS in different domains will become essential, providing many interesting challenges for both practitioners and researchers.